In this lecture, we, we discuss what is the method to trace the polar curve. Suppose the equation of the polar curve is given by r equal to f of theta, or it may be also theta equal to f of r. For tracing the polar curve, we take the following points. First point is symmetry. There are following symmetries in the polar form. First one, about the pole. If the equation to the curve remains unchanged by changing r to minus r, then the given curve is symmetric about the pole. For example, if we have given r square equal to a square cos 2 theta, and if we replace r by minus r, then minus r square is again r square. So this curve is symmetric about the pole. The first very important point is, in case of polar curve, we don't say x-axis and y-axis. Here we will say this part is called initial line theta equal to 0. Means x-axis is called initial line. This point origin is called pole. It is pole. And y-axis is called line theta equal to pi by 2, line theta equal to pi by 2, or sometimes we say that the line perpendicular to the initial line at pole. What is the second name? Either we say that line theta equal to pi by 2, or we say that a line which is perpendicular to the initial line theta equal to 0 at pole. So there are three things over here. Origin is called pole in case of a polar curve. X-axis is called initial line theta equal to 0, and y-axis is called a line perpendicular to initial line at pole, or simply we say that a line theta equal to pi by 2. So here we take three type of symmetry. The first symmetry is about the pole. The second symmetry is about the line theta equal to 0, and the third symmetry is about the line theta equal to pi by 2. Here, if you want to check the symmetry about pole, we have to just replace r by minus r. If the equation of the curve does not change, then we say that the curve is symmetric about pole. Now the second case, about the initial line theta equal to 0. If the equation to the curve remains unchanged by changing theta to minus theta, then the given curve is symmetric about the initial line theta equal to 0. For example, r equal to a times of 1 plus cos theta. So here, if we replace theta by minus theta, so cos of minus theta is again cos theta. So the equation of this curve will not change by replacing theta by minus theta. So we can say that this curve is symmetric about the initial line theta equal to 0. Now the third symmetry is about the line perpendicular to initial line through the pole, that is line theta equal to pi by 2. This can be checked in two ways. The first way is if the equation to the curve remains unchanged by changing theta to minus theta and r to minus r, then the given curve is symmetric about the line theta equal to pi by 2. For example, r square equal to a square cos 2 theta. Here, if we replace r by minus r, theta by minus theta, then the equation of curve will not change. So therefore, this curve is symmetric about the line theta equal to pi by 2. The another checking, suppose this is not true, then we can also check one more check we have. If the equation to the curve remains unchanged by changing theta to pi minus theta, then given curve is also symmetric about the line theta equal to pi by 2. Let me take one example. If r equal to a times of 1 plus sine theta. So here, if we replace this theta by pi minus theta, and we know that sine pi minus theta is sine theta, hence, by replacing theta by pi minus theta, the equation of the curve r equal to a times of 1 plus sine theta is remains unchanged. So this curve is symmetric about the line theta equal to pi by 2. So if we want to check the symmetric about the line theta equal to pi by 2, we have to first check the first part, theta by minus theta and r by minus r. After putting theta by minus theta and r by minus r, the equation of the curve doesn't change. We say that it is symmetric about the line theta equal to pi by 2. Suppose it is not happening, then we again check. Suppose it is happening, then there is no need to check the second point. But if first point is not happening, then we will try to check the second point. Means we replace theta by pi minus theta, and if the equation of the given curve remains unchanged, then we say that the curve is symmetric about the line theta equal to pi by 2. So this is all about the symmetry of the polar curve. Let us go to the second point. Second point is pole. Since we know that in Cartesian curve we have taken as a origin, but here origin is called pole. So here how to check the given curve passes through pole or not. So for any value of theta, if r equal to 0, then the curve passes through pole. Right, so if we have given any equation, for example, suppose we have given r equal to a times of 1 plus cos theta. So for which value of theta r should be 0. So we have to just put r equal to 0. So this is 0 a 1 plus cos theta. And it implies 1 plus cos theta equal to 0, means cos theta equal to minus 1 and cos pi is minus 1. So theta equal to pi. What it means? It means that theta equal to pi, for theta equal to pi, r should be 0. Therefore, this curve passes through pole. For any value of theta, if r becomes 0, for any value of theta, then we say that curve passes through pole. Otherwise, it does not pass through pole. Now, once the curve passes through pole, so what is the tangent at pole? So tangent at pole can be obtained by putting at r equal to 0. For example, here r equal to a times of 1 plus cos theta. We want to find out what is the tangent of the polar curve at pole. So what we have to do, we have to just put r equal to 0. Then we get the value of theta, theta equal to pi over here. So theta equal to pi is the tangent of this curve. Angle between the radius vector and tangent. With the formula tan phi is equal to r d theta dr, we can find phi and also the points where phi is 0 or infinity. Then we make a table values. We make the table values for theta and r. Then asymptotes, we will try to find the asymptotes if possible. And the last one is the reason of absence of the curve. Solve the equations for r and check how r varies as theta increases from 0 to plus infinity, and also when theta decreases from 0 to minus infinity. If for some values of theta r square is negative, that is r is imaginary, then there is no branch of the curve exists for that values of theta. If the maximum numerical value of r is a, then the entire curve will lie within a circle of radius a. So these are the different points which we have to use to trace the polar curve. In the next lecture, we take one example to trace the particular polar curve. Thank you.